Hello everyone, my name is Jay Gupta. I'm a computer science engineering graduate with a specialization in artificial intelligence and machine learning. I have 3 years of professional experience in data architect and data engineering field. I've also worked as a TA for deep learning for Neuromass Academy in 2023. In this brief video, I'll recap the concept of AutoGrad and its significance in deep learning. AutoGrad, short for automatic differentiation, lies at the core of many deep learning frameworks like PyTorch and TensorFlow. Essentially, it is a computational technique used for efficiently compute the gradients of complex functions, which is crucial for optimizing neural networks during training. In deep learning, we often deal with complex models composed of numerous layers and parameters. To train these models effectively, we need to optimize their parameters by minimizing a loss function. Gradient descent methods are commonly used for this purpose, where we adjust parameters based on the gradients of the loss function with respect to these parameters. This is where AutoGrad comes into play. Instead of manually deriving and implementing gradients for each parameter update, AutoGrad automates the process by dynamically computing the gradients through the computational graph that represents the network's operation. This means that developers can focus more on designing and experimenting with complex neural network architecture without worrying about the intricacies of calculating gradients manually. Now let's jump into the coding section where we will be building a simple computational graph by using a forward propagation and calculating the square mean error loss function. So here you can see that we have a class called simple graph. This class implements a simple computational graph. It represents a basic neural network with a single neuron. Then we are initializing with the help of a constructor. Constructor method initializes the graph with the initial values for weight, W, and bias. Both W and B are converted into PyTorch sensors with required gradients equals to true, meaning they will be tracked for gradients computation during backpropagation. So after that, we have a forward propagation function. In this function, we are taking the input value as a x, and we'll be calculating our prediction based on the x. So we'll be passing the input value x into the tan is activation function. So here we'll be calculating our prediction. So it will be like passing through the tan is activation function. So we'll be multiplying our input with the weight and plus bias. Since we are utilizing the pie chart, we'll be taking the tan activation from the PyTorch library. So yeah, okay. We are done. The next we'll be calculating our square loss, which is also called L2 loss function. In this, we are given two inputs, which is y true and y prediction. So we'll be calculating our loss as y true minus y prediction and taking the square root of this value, which will give our L2 loss function. So the next, we have given our feature as a tensor 1 and target is tensor 7. Okay. The next, we will uncomment this part and run. So in this section, we're creating an object of our class simple graph and passing two values as a weight as minus 0.5 and bias as 0.5. The next, we are calling the forward function by passing the input feature. And the next, we're calling this square loss function by passing target and prediction. Now let's run this code and see the output. Okay, so we're seeing for x equals to 1, input and y is equal to 7, which was our target tensor. Prediction has come to 0.0 and loss is 49. So you can see our loss is very high so that it was not able to predict the actual value. Thank you so much.